Good morning, everyone. In the day four on our GAN course on chalcogenide-based wastage memory for non-volatile data storage. So now we are going ahead with day four session. So now I request Dr. Andriy to start with his talk on phase transformation induced by ion and electron waves. Please.
Okay, good morning, everyone. Today we will continue our lecture, and I will be talking about phase transformation induced by ion and electron beams. So first, I will start with ion beam induced phase transformations. So ion beams, this is a very valuable tool to modify materials or also to induce some doping by implantations. This method is very uh, often used by the industry, and so the modifications of the surfaces and solids by ion beams can be made like by direct ion implantation, by ion beam mixing, ion beam assisted deposition, and plasma ion implantation. So I will not consider all of them. My focus today is on direct ion implantation. What is it? Direct ion implantation. This is a tool for modifying the structure and properties of solids. This is a non-equilibrium process, and it's accomplished by bombarding the target with a beam of ions in the energy range from the few hundred kilo electron volts to several mega electron volts. Here you can see a sketch of the processes which can be induced by ion beams. This is the energy scale, so ranging between 0.1 to 1,000 evolts. And what we can see here, we can see that the ion beams then can induce like implantation, displacement of ions, sputtering, desorption, uh, and other processes. But as I said, we are interested in this direct ion implantation, and we will see how this implantation can influence, impacts the displacement of atoms in our materials. So if you look to some data on projected range of ions as a function of ion beams, so here they can look how far the ions can penetrate into the materials. This is the energy dependent process, and also this is ion dependent process. So if you look here, the penetration depth of nitrogen, this is the germanium and this is the argon. So the nitrogen, this is the lightest element in this from this, and they can see that it can go into the GST 225 until high depth. So the germanium, it goes not so far in the solid. If they make ion implantation, there is also some losses of energy which can be induced by the ions. And here we see the energy loss independence on the energy, and here also for different energies, for different also species like nitrogen and germanium. And here nitrogen, it induced like electronic losses in the material, and germanium, it's induce more nuclear losses in the material. This is important to know because these two different processes, this results in the two different results. Like the electronic losses can result in the heating of the material, and it's important to know this. So now let us look to the some experimental results on this. So if you make material doping, if you want to modify the properties like conductivity, we can induce some elements into the material, and then they can tune the properties. So here this graph shows you that if they induce some nitrogen or oxygen into the material, that the conductivity here, we can reduce the conductivity of GST material. This is this line, dark line, black line shows you the undoped material, and here this nitrogen and oxygen, the doping like on the average 1.6 atomic percent, that it can reduce the can decrease the conductivity of GST material. Fluorine, it make reverse process. It increases the conductivity of GST material. Also interesting that the ion implantation, it also causes the change of crystallization temperature of GST material. Here we can see that carbon and nitrogen, it can increase the crystallization temperature of GST. Also, this is process, it's dependence on ion fluency. So for low ion fluency, there is no change in the crystallization temperature, and the increasing of doping and fluency, this the crystallization temperature of GST can be tuned and increased. In the case of carbon, this is really a really impressive effect. So you can achieve the values like 300 degrees C. For the boron, light element, and the oxygen, this effect is not so large. Also, doping influences the activation energy of crystallization. So if the activation energy of crystallization for undoped material, it's on the range of 2.9 eV, doping with nitrogen and oxygen, and also fluorine, it can increase this activation energy of crystallization, and also oxygen at high value of 6 atomic percent also increases the activation energy of crystallization. So as you can see, the material properties can be tuned by ion doping. Here we considered the low energy ion range. If we go to also consider some other interesting properties. Previously, the irradiated amorphous materials. Here, let us look how the crystalline materials behave. Here we consider the trigonal stable structure and this FCC roxal structure. And here there is again dependence of resistivity and irradiation. And what makes this irradiation, it change the properties, like here for roxal type, the resistivity here we see this is it increases, and for trigonal phase it's also increases. So here we see the transformation from the crystalline phases to the amorphous phases, because this value of resistivity, it approaches the value of for amorphous phase. Also, we can observe the transformation from metal to insulator. Again, for if you start with trigonal phase, you know already it behaves like metal, and by ion irradiation with particular fluences, this structure transforms to to the insulator here, confirming these results. But the state of the rock salt structure, FCC structure, it stays the same during this fluences. So here the TCR does not change. It stays always smaller than 0, and they know that this phase behave like insulator. And the TCR of trigonal phase is changing from positive value to the negatives value. Also, there are also some theoretical study which shows how this process, transformation process occurs. Here, this is the argon. This is again two structures, GST2 to 5, GST1 to 4, trigonal structures, and they studied how the gap filling. We know this structure consists of like van der Waals-like gaps, and here they considered how the gap filling influences the structure independence on the fluency. So at value of gap filling like 30%, so the atoms starting to move to the gaps. There is here the metal insulator transition, so the structure transforms most probably to the structure between rock salt and trigonal, and then at higher gap filling, the rock salt structure starting to transform into amorphous structure. So here also these results confirm these experimental results very, very well, and the transformation mechanism here based on the gap filling by atoms, which is induced by ion beams. So you can see here how the crystal structure also can be modified by ion beams. Now let us look how the higher energy ions impact the structure of GST. So here the materials was irradiated by fifth heavy ion irradiation. So the ion energy in the range 120 MeV, and here we have in this case if you use silver ions, then they induce mostly the electronic energy loss. Here, this is the dominant process. If they start the amorphous phase, and if this amorphous phase is irradiated by ions of different fluences, here like 10 to the 11, 10 to the 12, and 10 to the 13, here one can see the transition from the amorphous to crystalline phase. In the case of if this amorphous phase is irradiated, the ions, antimony ions, this energy, they induces mostly the nuclear energy loss in the system. Here, the system, amorphous system, it stays in the amorphous state even up to implantation of 10 to the 14. But this is the Raman spectros. If we look to the amorphous phase, there are two different peaks. One is situated at 129, one at 150. There is a slightly change in the structure of initial amorphous state. So there is here some change in the local structure of amorphous phase, but there is no a huge transition to the crystalline phase, as in the case of the electronic energy losses, as in this case. So if they also make radiation with slightly higher ion energy, with very heavy ions, like this energy 1.64 GeV gold ions, they also induces electronic energy loss into GST2 to 5. And here the different structures were irradiated, like amorphous and trigonal, and also germanium-rich GST, to see the influence of structure and ions on the phase transition. So in the case of amorphous state, and here there was a transition to the crystalline state starting at the fluency of 10 to the 12 cold per square centimeter. Here there is a transition. Here, if the irradiate crystalline phase, there is no phase transition for the crystalline phase by swift heavy ions. For the irradiation of a germanium-rich alloy, which has crystallization temperature of 250 degrees C, also there is no amorphous to crystalline phase transition. And if we irradiate the FCC crystalline phase of germanium-rich alloy, there was possible to transform this crystalline phase, FCC phase, to the amorphous state at these fluencies. So what this energetic loss do to the structures? Here, if we consider amorphous material, the ion implantation, the ions they transform the energy to the electron system of the GST, and then this energy to transfer to the lattice via electron phonon interaction, and then the system locally heats up, and then transform to the crystalline state. This model is so-called spike model. And in the case of irradiation of crystalline state, like a cubic state here, the irradiation causes simply the disorder in the system. So because there are several vacancies here, and then if you induce enough disorder and lattice distortions to the system, we can transform from crystalline to amorphous state. So now also let us look for ion irradiation at 80 MeV, also swift heavy irradiation. They causes also electronic energy loss. Here again, the S-deposited phase was irradiated, but there was no phase transition using these ions. But there was a change in the band gap for different fluencies. Like this is amorphous state, and we have band gap of 0.667 eV, and then this band gap is changing, it's reducing. So we can see again, although the system stays amorphous, there is some structural changes in the amorphous state, and it goes more closer to the values more closer to the crystalline phase. We know that the crystalline phase, it has like band gap of 0.5 eV. So they have reduction of band gap, and they can see how the ions can also modify the electronic structure and properties of the materials. Also, some conclusions to this swift ion irradiation with high energetic ions. So for low energies, like we irradiated by different energy, starting from GeV to MeV, and also here to MeV. Here we in all cases observed electronic energy losses. For the highest value, it was like 34 kilo electron volt per nanometer, and then it was changing and reducing. For these both cases, we found the amorphous to crystalline phase transition, and in this case, the flow energy, electronic energy loss. Comparing the both cases, there was no amorphous to crystalline transition, and this shows that there is some free shot value necessary for this amorphous to crystalline phase transition. To some application of this ion beam irradiation, how the material properties can be adjusted or even created by ion beams. In this case, the ion beams from the FIB focused ion beam system was used like it has ion beam energy of 30 kilo electron volt. This is standard tool, as I said in the previous lecture, that it's standard tool for TM specimen preparation, and it can be used for research. So by using this focused ion beam, because we know from previous results that ion beam can induce the amorphous to crystalline transition or from crystalline to amorphous. And so it can be maybe used to modify the surface of GST and can be useful for creating a new, let's say, optical devices. In this case, the metasurfaces were created by using focused ion beam. So what is metasurfaces? Metasurfaces is a two-dimensional artificial material consisting of sub-wavelength structures arranged in a planar or 2D pattern. So by using such a focused ion beam, you can make lines of crystalline and amorphous materials. And this is top view. This is the cross-section, crystalline, amorphous. You can create like a two-dimensional pattern of structure, which arranged like in planar here. So, and this leads to the change of optical properties, like shown here. This is for non-irradiated material, and this is for structured material with different spacing between. And we show that the reflectance is changed a lot, and so these ion beams can be used to control locally the properties of phase change materials, and also you can create different types of structures by using focused ion beam. So as small conclusions on ion beam irradiation. So ion beam irradiation, this is a very powerful tool to achieve engineering of the physical properties if you can properly adjust the irradiation conditions. So now let me move on and to look to electron beam induced phase transformations. So electron beams, as we know, we can create it in transmission electron microscopy or also in scanning electron microscope. There are also special accelerator where they can use. But here I consider mainly how to modify the chalcogenides using the TM or SEM. And let me first consider some basic properties regarding the electron irradiation damages which can be induced by electron beam in TM. So here in the TM they have mainly two processes like elastic and inelastic electron scattering. The elastic electron scattering and inelastic can lead to the electrostatic charging, also to atomic displacement and ion beam sputtering. This process, inelastic scattering, can lead to the specimen heating, also to structural damages, mass loss, and deposition. Here, however, mainly we see in TM this atomic displacement process and specimen heating. Structural damages also present, but we will focus mainly on this specimen heating and atomic displacement, how to use these two effects to modify the properties of GST thin film. So now let's look to the atomic displacement. Atomic displacement, this is so-called knock-on damage in the material. So knock-on damage, it arises from elastic scattering and of electrons, and the electrons they transfer the energy to the atomic nucleus, and this amount of energy which transferred to the matter, it can be described by this equation, and the maximum energy which can be transformed here is described by this equation. So there, here in this equation, A, this is atomic weight mass, U, this is atomic mass unit, and this is the electron rest energy. So the knock-on damages, what they make in the material from the damages, if the electron come to the lattice, or electrons come to the lattice, they can just kick out the atoms from your lattice, either to shift to the neighbors or just to kick out from your material, and then you can see some damages like amorphization, or even some holes in your specimen. So to achieve this knock-on damage, you should overcome so-called value of displacement here, maximum value of energy displacement, and this value of this displacement, it's also material dependent. We can make some rough estimation on this, and we can see here that the displacement energy also varies with the type of atom. So here somehow for graphite it's 30, for aluminum it's 17. But if we then insert this ED value to the E0, this is the threshold excitant energy which requires to shift the atom from the lattice. It's now we can see that it depends on this E0 and material properties. So for graphite we need only 140 kilo electron volt, for diamond 300, for aluminum 180, and so on. So we see that it depends on the energy, and if we have some light elements, we can easily kick or destroy the structure in the TM. Also some electron beam heating. This effect is caused by inelastic scattering, which involves collision between the incoming electrons of similar mass of TM specimen, and the temperature heating in the TM. It's described by Fisher models, and the temperature heating it's a function of beam current, also thermal conductivity of the specimen. This is the delta E. This is the total energy loss per electron. D, this is the specimen thickness. B, this is the specimen radius, and R0, this is the beam radius. We can also estimate some beam heating induced in the specimen. We can take the like for estimation like strontium titanate, and we can look here how the heating, how the electron hits our specimen. Here, of course, there is the delta D is calculated. This is the difference in the temperature, shows the temperature rise in your specimen. And so this is thermal conductivity of the specimen. This is one of the main factor here. Also beam current, but if we fix beam current and electron beam energy, but we can vary a little bit the thermal conductivity of strontium titanate, which is like on the range of 10 watt per millikelvin. If they use such large conductivity of the material, then we do not have an increase in the temperature in the specimen. But if the reduce the thermal conductivity of our material, like to the several order, 0.0.1 watt per millikelvin. We can see that at a probe current of 30 pico amps, we have like heating on the average of 50 Kelvin. This is not so high increase of the temperature for this specific material, but for some another substances like GST, this value can be different because of this kappa. It can be also electronic thermal conductivity can be also different. So now let us look to the some data of electron beam interaction and specimen. So by electron beam, it's possible to induce crystallization of amorphous phase change materials. So here we can see this is the Blu-ray, this is the optical material, and here we see the crystalline phase of germanium antimony material. And here this part, this so-called amorphous mark, and by electron beam irradiation, this amorphous mark, it starts to crystallizing from the edges between here from these edges between amorphous and crystalline, and so after time of this is 60 seconds to 200 seconds, 220 seconds, we can see that after some times these amorphous areas they became crystalline. So in this case, this crystallization process was achieved by 120 kilo electron volt electron beam, and from such data, it's possible to also to extract some interesting data like a crystallization speed, and what we can see that the crystallization speed of this material, it depends on the current density. So at low currents we see a low crystallization speed, at larger, and this also gives our idea how the current density can influence the amorphization and the damaging processes in the TM. Also, this the effect of crystallization of amorphous mark. Here it was explained by heating effects. So because of electron beam interaction, there are some heating effects, and they leads to the crystallization of this material. So now let us look to the electron beam induced crystallization of amorphous phase change material. Here in this case, GST225 was studied, and here the 200 kilo electron volt electron beam was used. Here at the starting point, we see amorphous GST225. This is the electron diffraction, shows diffuse rings. It's a signature of amorphous material. And then after some time, after 10 minutes of electron beam irradiation, you can see the formation of crystal, like nucleation. In the electron diffraction pattern, you can see here, or it's FFT, fast Fourier transformation, you can see the formation of additional reflections here, like dots, and this is a signature of crystalline lattice. And after 24 minutes, there are also here formation several crystallites, and then here the process is proceeding, and the formation of more crystallites in this GST225 material. So because this materials is nucleation dominated, we don't see the growth of these crystallites. So rather they see the nucleation of our additional crystallites. Here you can see more one, these dark areas here and here, so and more. So this electron beam can induce crystallization of your material. If you do TM work, you have to be aware of this, and you have to adjust the temp settings to not to induce the crystallization, unwanted crystallization of your material. Also, the electron beam can modify the crystalline structure of GST material. In this case, we start with cubic lattice, and we use focused electron beam in the transmission electron microscope. We know from the tutorial we can use the parallel beam, or we can make a focused electron beam and laten it on our crystalline specimen. So we make really like a line, like a line here, or the beam is like a spot, and the size of the beam on the average of the atomic size of our material, like 100 picometer. And if you do like this, and if you scan along the germanium and antimony cation layers, we know already that they contains around 20% of vacancies. If you do like this here, if you scan the electron beam here, and then on this place, we can write so-called vacancy layers in our structure. It's nicely shown here. This is the lattice before irradiation. It shows typical FFT pattern with main reflections. And here, after the irradiation, local beam, the change of the structure, we can see the formation of these dark lines. And these are the vacancy layers. This also can be seen FFT patterns. We have the formation here, additional lines on 111 planes here, and this is the signature of the formation of these vacancy layers. We can also bring back our modified area to the initial structure. If they make electron beam irradiation by a little bit larger beam, then we can transform this modified area to the initial area. By this, we can create different nanoscale structures in the material, like here periodic vacancies layers, where we have building units with 5 tellurium layers, which corresponds to the 2 to 5 structure. And what happens here in the case of such electron beam irradiation? So we know that this GST that contains 20% of vacancies on cation sites, and now if we heat up a little bit these layers by electron beam irradiation, then they move the germanium and antimony to the neighbor sites here and here, and then we create so-called vacancy layers. And then if you again the irradiate this structure, this vacancy layers by broad electron beam, we again induce some heating effects here to these layers, and then the cation they moves back to the vacancy layers. So again, we have here atomic displacement of germanium and antimony towards the vacancy layers, and this is induced by electron beams during most probably inelastic interaction, as I said, because of electron energy transfer to the electron sublattice of this GST225. So now let us look also one interesting effect, also crystallization of GST225. But here we can make the crystallization from the interface, and in this case we can make like epitaxial recrystallization of amorphous GST material from the crystalline interface. In the example above, I showed the crystallization from the amorphous state, and we have random formation of crystallites. But here, if we have a crystalline interface, we can induce the oriented growth, oriented recrystallization of amorphous state. This is so-called epitaxial recrystallization. Here, if they heat up this area by electron beam, this is, you can see, this is nanoscale area, like 10 by 3 nanometers. If they heat up this by electron beam, we can produce such a small nanowire here. Then, if we again heat up this area, we can produce larger nanowire. And if we we can also look this in situ. So if you just created like a nanowire of this size, then I can show that this is true. You can take, this is the real image, you scan here, nothing happens. And if you irradiate the area of this, let's say, nanowires, then it starts to grow directly without any incubation time or so you see nicely epitaxial growth of this nanowire. So what we also see here, that we used very small window for electron beam heating of this area, but the resultant structure is like doubles of this area, and this shows that the heat also goes to the left and to the right, and also causes the formation of such nanostructures in the amorphous phase. So here you see this is irradiation after 30 seconds. Also, each image is after 30 seconds. This we can also use this effect for creation of different structures and sculpturing of the GST, of the amorphous GST. So here, this is one example. We could create from the interface like a head of the duck. So we produced first the crystallization. We allowed to crystallize the material in this direction from the interface. But if we have here crystalline interface, we can also make crystalline structures in this direction. So you can route different structures in your amorphous material. Also, we could make crystallization in an amorphous matrix, as was done before for gallium antimonide. Here, this is the GST225, and we start with amorphous material, and we irradiate it here by electron beam. But the crystallization here takes longer time because we have no interface, no template, and the crystallization here takes more time because you need some time, and it requires around 90 seconds. In the previous case, we can crystallize the same on the same volume using 30 seconds. Here we can also quantify, we can do different experiments using such crystallization. And we can see that if you use interface for the crystallization, the growth rate is much higher compared if we just allow to crystallize the GST from the amorphous matrix. So here we see that the interface-assisted crystallization is faster than nucleation-dominated crystallization. And here we also see, due to this dependence, linear dependence on the growth rate via electron beam current, that this is the thermally driven process, and this is because the transition of electron beam to the energy from electron beam to the material, and that causes the local heat of the lattice. So here also it shows some TM results on this process, on also some the IMD simulations, unpublished simulations. So what we can see, what we can study the structure of the amorphous state at the interface, and by using this fluctuation electron microscopy, we can see the order at the interface and compare at different places. And according to these results, the order of the amorphous state here close to interface is much higher of the amorphous state than in the middle or at the top. And this is one of the reasons why this crystallization is faster than crystallization solely from the amorphous phase. This can be also confirmed by IMD simulations. Of course, we are not on the same time scales. Here we are on picosecond time scales. Our experiments on the second time scales, but it can give like little bit feeling of this process, that the simulation and experiments are in line. So if you start with the system like crystalline here and amorphous stack, and if we heat up this stack to the 600 Kelvin, at this temperature we can crystallize the material. We can see that after 40 picoseconds, this stack, this system is already crystalline. It's highly ordered system, confirming experimental results. But if you take the system without interface, crystalline interface, then after 40 picoseconds, the system stays again still in the amorphous state, and this requires more time for the crystallization. So again, simulation experiment are in good agreement, and the nice here that the epitaxial interfaces can speed up the crystallization. So now let us look to the reverse process of amorphization process, so transformation from crystalline lattice to the amorphous lattice. Here this process is occur on more longer time scale, so it requires like more than 1 hour. If you start from the cubic, from FCC material, you can see here this is vacancy ordered structure or trigonal structure. This is HRTM image, so you see here some lines, maybe from the lattice spacing, maybe corresponding to the layer structure, but they claimed it should be cubic. So after 40 minutes, there is a transformation of this cubic, of this area, to the amorphous state, and after 60 minutes, more and more, and here after 80 minutes, you see there is no reflections coming from the crystalline lattice. So they used a 200 kilovolt electron beam, GST 1 to 4, and this is the dose rate what they used. Um, they also estimated the maximum temperature rise during this experiment, and they found that it's like 220 degrees C, and this temperature is well below the melting temperature of GST 1 to 4, which is on the range 650 degrees C. So this transformation, crystalline to amorphous transformation, is most probably driven by the disorder, by the formation of by atomic movement and high displacement in the system, which results in the amorphization of the materials. Again, we know if we can induce large enough distortions to the system, we can go from crystalline to amorphous state. And maybe this is a nice example how does it nice example of this process of the theoretical results from the lecture yesterday. So now let us look to the electron beam modification induced by a scanning electron microscope. Here, this is the also another phase change materials which can be used for optical application. This is a typical antimony sulfur glass. It's not like the phase change materials. It has a little bit different properties and bonding. It's more covalent, more stable glass. But this is interesting glass in the sense that you can make also some structural modifications of this glass. So what you can see, what you can do if you start with amorphous material, you can induce the crystalline areas to this material by using scanning electron beam. Here we talk about energies which are much lower compared to the TM. This is like 30 kilo electron volt, and this modification was achieved at 20 kilo electron volt, and at beam currents 60 nanoampere. But the beam currents here are much larger compared to the TM used for this experiment. So by using this SEM, they could also create some interesting features on the surface. You can see some letters, some logos of their institute or something like this. So it shows the transformation from amorphous to crystalline and creation of some interesting feature. And here, by using electron microscopy, one can see the crystallization or amorphization of such structures. So now let us conclude this part of my talk. So here the energetic beam of electrons can provided by transmission electron microscope or scanning electron microscope. The electron beam used in these two microscopes can cause changes and damages in the surface or bulk structure of the specimens. The damage is classified on the type of electron scattering, like elastic scattering and inelastic scattering. In TM, the energy gained by TM specimen can induce phase changes like amorphization and crystallization. Also, the focused electron beam in TM can be used for local modification of crystalline lattices. And electron beam in TM and SEM can induce amorphization, crystallization, and atomic movements, as well as surface pattern and phase change materials. And so the focused electron beam is a very powerful tool to tailor disorder in phase change materials, but also the electron beam irradiation can be also used for modification, not only these materials, but in other like oxide, strontium, titanate and silicon, even silicon. So I think this is summary of this two part of my lecture. Now we have some time for questions.
So, any questions? If you have any query, you can ask to speaker. Anyone? I think we should go ahead. I think they can discuss later on also if
Okay.
something is.
Then should we make a break?
Just a break.
Break,
Yeah.
okay.
Okay, so then we'll have a short break of 10 minutes and then quickly we'll come back. There is a tea. Okay, you can have a tea and come back. Okay, thank you.